Welcome back with another lecture from organic chemistry. It's 1:05 a.m. Saturday. I'm sitting in my office, and the nice thing, working so late is that you can play loud music. Nobody's gonna bother you. My neighbor, he's not in his office, and as usual, as a Middle East person, I have my tea close to me, and that's the one actually it's gonna keep me awake. I can't drink coffee, it's too late, but tea is my best friend. Okay, let's go after almost the last part of the IR spectroscopy, the IR spectroscopy, and we want to know. We want to review two actually concepts when it comes to the spectrums. One is going to be intensity of the peaks, and the second one, it will be the shape of the peaks. Okay, in this case, I see two peaks. One is a weak signal, and the second one is a strong signal. When do I get a weak or strong signal? Okay, remember, whenever we are talking about vibration in IR, mu or polarity cannot be equal to 0. That cannot happen. If mu is equal to 0, then we say it's not gonna, that stretch or that vibration is not gonna be active in IR. Okay, and I'm gonna show you some example. Okay, so let's start with this. Okay, so say we have such a molecule. Okay, so the molecule that I'm gonna review, it will be CO. Okay, so carbon attached to oxygen, and I'm going to introduce another oxygen. Let's go with different color. Okay, and how many types of vibration I can have? First one, both bonds are stretching or maybe contract. Okay, sorry, stretched maybe or maybe contracted. So one case, the bond, let's make them really lengthy, or make them really short. Okay. In both cases, I'm going to say this oxygen is going to pull to the right side. So I get F1, which is going to cancel by F2. And I have the same forces here. So in any type, in any mode, that vibration, okay, is not going to be active. And that type of vibration, we call it symmetrical. So when you have two technical bonds getting close to each other or far from each other, and they are made of same elements, like carbon, oxygen, and we say because mu, it will be equal to 0, it will be not active, not active, okay, not active in IR. Guys, and how about the second? Okay, the second case, let's keep one bond, okay, let's say as it is. Well, we are increasing length of the second one. That's one way. Okay, so this one is going to the right side. Okay, and maybe this one is getting shorter. Okay, and in this case, because the length are not identical and length are not the same, F1 is not gonna be equal to F2. They will not be equal. Okay, and so that means mu is gonna be something bigger than 0. And of course, you can draw this one, this time increase this one, but let's say keep the second one as it is or contract it. Okay, again, this force, call it F2, is not equal to F1. So mu is going to be bigger than 0, and that's non-symmetrical stretch. Okay, non-symmetrical. If it's non-symmetrical, and the molecule will be active in IR. So this one, it will be active in IR. Okay, and what's the last one? Last case. Okay, remember, you have a carbon that attached to two oxygens. So that means there is a bond angle between, and the bond angle is 180 degrees. Okay, how about this? What if we, like play with the bond angle? Let's say we put one carbon here attached to this oxygen, keep the second one there. Okay, so now that this bond angle is changing and we call it bending. Okay, so the bond angle is changing. While the bond angle is changing, you can do this. Okay, you can say, while the bond angle is changing, one of the bonds is getting bigger. And let's say the second one is getting smaller. And yes, the bond angle also is getting less than 180. Okay. The chance to have both, both of them or three of them happening at the same time. Okay. One bond is getting bigger. The second bond is getting smaller. And at the same time, they are moving toward each other. It's kind of like, it's hard to have all of them happening at the same time. It's not impossible. It can. And in this case, mu, it will be bigger than 0. So that means it will be active. Okay. Same thing there. Mu, it will be bigger than 0, and they will be active in IR. So you can have asymmetry called stretch, or you can have bending, or bending and stretching at the same time, and that's gonna give you a signal in IR. Okay. So now let's go back to our slide. Okay. Now, when we are talking about polarity, we need to have positive and negative charges in a distance far from each other. Okay. The more positive and negative charges you have, okay, the more positive negative charge or bigger charges you have, the higher chance to get higher polarity. And also, we need to have those charges far from each other. We need to have a positive pole, a negative pole, and a good distance far from each other. In that case, we were going to say we have a permanent polarity. If we have a permanent polarity, we're going to see a signal in IR. So in this case, you see carbon, okay, attached to oxygen, second time carbon, second one carbon to carbon. Let me, okay, present it here. So I have a carbon with sp2 hybridization. I have the same thing here, sp2 hybridization. And that carbon, red one, okay, it has sp2 hybridization. So I have two carbons with sp2 hybridization. Of course, electronegativity of those two carbons are going to be really close to each other, almost identical. Okay, why say almost identical? Because that one, it has two hydrogens, and here we have methyl group. So those two carbons are not 100% identical, but electronegativity almost the same. Okay, almost the same. Okay, well, there we have oxygen with the sp2 hybridization. So I have carbon attached to oxygen, and okay, in both cases we have sp2 hybridization. But for sure, electronegativity of oxygen is way higher than electronegativity of carbon. So this bond is really polar, okay? It's really polar. And because it's really polar, you see stronger signal here. Okay, the signal is going to be stronger than, the double bond of carbon-carbon. So polarity is going to affect the technically this intensity of the peak in IR. Okay, anything that make the molecule too symmetrical, okay, it will minimize or reduce number of signal in IR. Listen carefully. The molecule with huge number of symmetry, like elements. Okay, let's say you have a mirror. Okay, you put a mirror and you chop the molecule to two half identicals. Like, for example, in this case, I can put a mirror here and cut the molecule to two in half, identical half. In that case, we say number of peaks will go down. Why? Because you will get many stretches or bending that they are, identical, and mu it will be equal to 0. So even we have a double, okay, we have a carbon we have a double bond between two carbon-carbon, I don't see a peak between 16 to 1800 for double bond of carbon-carbon. Okay. Why? Because the molecule is too symmetrical. Okay, it's too much symmetrical. And what's that peak? That peak is a CH. Well, carbon, it has sp3 hybridization. Okay, so if you have a symmetrical molecule, okay, you have a symmetrical molecule, you will see less number of peaks, and some functional group maybe it don't show you any peak because molecule is symmetrical. Okay, so highlight that. Okay. Now, next one is going to be the shape of the peak. Okay. If you have a molecule that involved in hydrogen bonding is going to make the OH or NH or FH bond bigger or smaller. Okay, listen carefully. Bigger and smaller. That bond, it keeps changing a lot. Okay, size of this bond is going to change a lot. So you will have a big range for OH. Why do I keep saying that it's going to change? Because the lone pair, it will be donated to hydrogen. And hydrogen, so let's rewrite. Lone pair is going to give 2 electrons technically inside lone pair or oxygen is going to donate 2 electrons, okay, or lone pair inside the sigma star orbital of technically hydrogen. And hydrogen is going to give off those 2 electrons to oxygen. Okay, so we are trying to break the OH bond and form a new bond here. Okay, new bond there. Okay, yes, that's not gonna it's not gonna break 100%. Okay, it's not gonna, but we are establishing some connection between oxygen on the right side and hydrogen, and that's gonna change the bond length of OH. And because it's changing, you will get broad range for OH. If you get such a peak, broad one, that's a sign that you have OH. Okay. If there is no hydrogen bonding, signal, it will be really narrow. Okay. So having a broad peak higher than 3200, that's a sign that you're dealing with OH, okay, or H that attached to oxygen and is acidic H. Okay, is acidic H. Why do I say acidic? Because it's going to involve in hydrogen bonding. Okay. Now, how can I, kind of like make it narrow? Anything that reduce number of hydrogen bonding, it will make the peak narrow. So if you dilute it really, like dilute it to high, like with a huge amount of solvent, a solvent that is not going to involve in hydrogen bonding, in that case, technically your OH signal, it will be narrow, and from broad shape, it will turn to narrow shape. Okay, but your solvent should not be able to get involved in hydrogen bonding with the OH. Okay, so as you see here, I have OH. Okay, I have OH that is free as it's not involved in hydrogen bonding, and the shape is really narrow. But if you introduce solvent and that solvent is capable of generating hydrogen bonding, then the peak, it will be broad. Okay, the more hydrogen bonding you have, or the more site for hydrogen bonding involved, in that case, you see you're going to see a really broad range for OH. Okay, so this range technically is started from somewhere, let's say somewhere from here, if we start, until there. Okay, and it's covering entire of that range. So I'm gonna say we have OH. Okay, and as you see here, we have 2 sites for hydrogen bonding. One is here, and the second is there. And of course, because we have carbonyl group, you have carbonyl group here. Let me highlight a different color. Those carbonyl groups are going to show up somewhere there. So in this case, I have two spectrums, and I'm going to try to, you know, like highlight the functional groups here. The first one, okay, I'm going to find 1500, and this is 1500. Okay, let's just simply go until here. Okay. And higher than 1500, I will try to highlight the peaks or the functional, the main peaks that I have. Okay, one peak that I have is here, and another one is there. Okay, so clearly we have CO. Why CO? Because it's showing up between 1600 to 1800. And that can be CO. Next, I see this peak, rod peak. That rod peak is technically showing me that I have OH. And how about this area? Okay, I have no peak here, so I'm going to say no OH. And how about this peak? That peak is CH, while carbon has sp3 hybridization. Okay, so the top molecule is a molecule that has OH and also carbonyl group, and the second one, it has just carbonyl group. So this one, it can be carboxylic compound, a compound that has carbonyl group and OH and attached to something. Well, the second one, the only thing I can say about it, the only thing is that I have R and I have carbonyl group there. And okay, do I have H or this one attached to, okay, another R group? Okay, because I don't see a peak. I don't see a peak around 3100, and okay, 3100 for this, for hydrogen that attached to a carbon with sp2 hybridization. I don't see it, CH vibration here. I'm going to say that cannot be the correct answer, and this might be the correct answer. So that second one, it will be carbon, it will be ketone, while the first one, it can be carboxylic acid. And the correct answer for them, here you go. The first one is a carboxylic acid, and the second one, as you see, I do have a carbonyl. Okay, I do have a carbonyl group here. Okay, but it's not, okay, it's not what do you call it, it's not just R. Okay, it's showing me that I have oxygen. Okay, I have oxygen here attached to it, attached to the carbonyl group. So this one is technically is in ester, and it's really hard to, okay, hard to identify whether this one is just a carbonyl or we have no oxygen. Yes, you can look for this region, okay, but with IR, okay, with IR mainly you can say whether you have OH, yes or no. Do I have carbonyl, yes or no? But tracking that region to find whether we have a carbon-oxygen bond, it will be hard, okay? And I don't expect my student really to grab a magnifier and search for, you know, like a technically signal in this region, okay? I will try to give them more data to understand whether this is a ketone, aldehyde, or something else.